I'm on a webcam. Just that's right.
Hello and welcome to this IChemE Global Awards 2021 webinar. The IChemE Global Awards celebrate chemical process biochemical engineering excellence and are widely considered as the world's most prestigious chemical engineering awards. Today we will be revealing the winner of the IChemE Industry Project Award sponsored by Silverfield Limited. This award recognizes the best industry project undertaking in the last 3 years. Before we check out the contenders, let's hear from our sponsor. It's Silverfield Limited's Chief Process Engineer, Elizabeth Cook.
Hello everyone and welcome to this session. Silverfield Limited is responsible for the safe and secure operation and clean-up of the Silverfield nuclear site, and in doing that we employ chemical engineers right across the life cycle, from strategy and studies through all stages of project development and through into commissioning and operations. I'm really proud of the way that our professional chemical engineers discharge their services across that life cycle. And we also have a number that support environmental remediation and nuclear decommissioning projects to enable the cleanup of the Silverfield site. In terms of our support for these IChemE awards, we've been supporting these awards now for 15 years, and I'm pleased to be able to be here to announce this year's winner of the industry project.
Thank you, Elizabeth, and thank you once again to Silverfield Limited for its support of the IChemE Global Awards. Our awards judging panel has been working hard in recent weeks to review and rank all of the entries, and here are our finalists. Corteva Agriscience, a joint entry from Dow Polyurethanes and Cell Foam Solutions. Johnson Matthey, a joint entry from the National Institute for Innovation in Manufacturing Biopharmaceuticals and Bioforum Operations Group. Another joint entry from Chezang High Matter New Materials, Ningbo University and University College London. And finally, Saudi Aramco. All our finalists have been invited to join us today to tell us more about the work and to answer your questions. You can get in touch throughout the presentations using the GoToWebinar questions box on screen. So let's get started with our first finalist representing Corteva Agriscience. It's Greg Whitaker.
Thank you very much. I'm excited to represent Corteva Agriscience in the IChemE Awards. Corteva Agriscience is committed to the development of new crop protection products to help farmers sustainably increase the yields of their products to help feed a growing world. Arylex Active is a new active ingredient that stands out from other synthetic herbicides in its ability to provide superior efficacy at very low dose rates. It's a new mode of action that provides fast, effective control of very difficult weeds that can reduce crop yields and can also control resistant weed species. Arylex has a very favorable environmental profile that's enabled by its rapid degradation in both soil and water. Arylex is used in a variety of geographies around the world in a large number of crops. And an important societal benefit that Arylex is poised to help provide is in the control of invasive ragweed in Europe in particular. Ragweed is a weed that is indigenous to North America, but has spread to Europe and is also projected to expand its footprint across Europe due to climate change. Tens of millions of people in Europe currently experience severe allergic reactions to ragweed, and the ability to control this weed, which causes a public health issue, is an important societal benefit of Arylex. The manufacturing process to develop Arylex involves a key step which utilizes a precious metal palladium catalyst to form the bond between the two rings of Arylex. And in developing the manufacturing process, we had to perform this chemistry using this expensive palladium catalyst, and efficient use of palladium was key towards the commercial value of this product and its ability to be used by farmers. However, what we found during process development was that in order to use low levels of palladium, we were forced to use a 4-step launch process, which is shown on this slide, that we used for commercial quantities up through launch. And that process requires the use of a protecting group in order to get low levels of palladium. This adds 2 steps to the manufacturing process to install and then remove this protecting group. So we use that process through commercial launch and registration. However, at the same time, we were investigating the fundamentals of this catalyst system, and we're able to identify conditions that allowed us to eliminate this protection deprotection step to make Arylex directly through a 2-step process as shown here. By applying the principles of green chemistry, we were able to decrease waste, reduce our production cost, and eliminate these 2 steps in the process. The business value of this direct coupling process is shown on this slide. It allows a 75% expansion of manufacturing capacity in the same plant with a 10% decrease in manufacturing cost. That decreased cost allows Arylex to be used in lower cost crops, that it's expand its use into other geographies and crops. And for society, importantly, this 2-step direct coupling process, which is now used in our commercial manufacturing, generates 50% less waste, which translates into the elimination of 5,000 tons per year of hazardous waste that's generated by the process. So in addition to Arylex being a highly sustainable crop protection product, our manufacturing process has an excellent environmental footprint. And with that, I'm happy to answer any questions, and thank you for the opportunity to describe our direct coupling process.
Thank you, Greg. It's now time for questions. So if you'd like to know more about our first entry, now it's the time to get in touch via the questions box. And whilst I give you a moment on that, don't forget there are more IChemE Award webinars coming up throughout the next couple of weeks. So you can find all the dates and times by visiting icheme.org/global awards. We don't appear to have any questions. And thank you again very much for getting things started, Greg. It's time to move on to our second finalist. Next up, representing the joint entry from Dow Polyurethanes and Cell Foam Solutions, please welcome Gretchen Bayer.
Hello very much. Thank you for the opportunity. Really appreciate the ability to share here. I'm Gretchen Bayer. I'm actually representing Yasmin, who had a last-minute conflict show up. And so what we are, the invention here is some breakthrough polyurethane for comfort applications. And so just for those of you who might not know about polyurethanes, they're a two-part chemistry, part A and part B. And the innovation behind this was really both on the chemistry front as well as on the process to achieve the final outcome. It's got some amazing properties as far as this goes. It's low pressure, it's low temperature, there's no catalyst, no exotherm, and a lot of tunability to make different kinds of products. So some of the applications is high performance bedding, specifically starting with pillows. So that would be a foamed application. We also have some personal care, foams that can be used for makeup application and things like that. Coatings is another use we see on the horizon, as well as adhesives or other kinds of elastomers, as far as that goes. What's unique about this is that it combines the ideal properties of the two incumbent types of polyurethanes. There's hydrophobic polyurethanes, which is excellent for mechanical strength. And then there's hydrophilic polyurethanes, which is great for thermal comfort and it's like material safety and sustainability of the material properties. So this breakthrough polyurethane really combines the features of both of those. And you see some of these comparisons in these figures. So here, this is the hydrophobic one. You see liquids beating up on it, whereas with our new polyurethane, there's quick wicking. Here again, you see our foam maintains its foam structure, whereas the hydrophilic easily compresses and stays compressed. So you can imagine neither one of these would be good for bedding applications. And this is also a graph just showing the temperature effects as well too, the cooling and for the heat conduction. This is the actual foaming process itself. And so again, we've got this novel chemistry. The foaming is typical polyurethane foaming. Here's the reaction here. And it uses standard process equipment as well too. So it's easy to just use existing equipment. So we've got mixing, then you pour mold, and then it goes through a drying chamber and cut and process. And again, these photos here really just show you can make, discrete parts, or you can make more continuous, coated type of materials with this as well too. I have a short video I'd like to show. We'll see if it works. And if it doesn't, just let me know. But this is also an illustration of some of the mechanical properties. So here you see the compression tests. Let me go ahead and make this full screen. And so not only compression, but it can be put in the oven. And when this is taken apart, you can see that the resiliency there. Here is a comparison of tear strength. So this is a conventional material here. You're going to see it rip pretty quickly, whereas our new material continues to, have elasticity there. Another demonstration comparison here of the typical hydrophobic foam. You see how it almost breaks immediately. The earlier one was a peel test. This is more of a the whole structure test. And this is again an example of the wetting here, which is important for these applications, both for breathability and for comfort. You saw this photo really on the earlier slide. And, you know, in addition, heat flux is important. And you see the benefits here, higher heat flux. So with that, just really like to thank you for the opportunity to present. Wish I could say more about the chemistry, but that's the challenge with the industrial projects. But thank you.
Thank you very much for that presentation, Gretchen. Once again, it's time for your questions. So if you'd like to get in touch, please do so via the questions box now. And whilst we wait, the winner of this award will have a chance to lift the second prize before the end of the month. All our team winners qualify as finalists for our top prize, the Outstanding Achievement in Chemical and Process Engineering Award. We will be announcing the winner of that award on Friday, 15 October. I don't see any questions coming in, so thank you again, Gretchen. We are going to move on to our third finalist of the day. It's Johnson Matthey, and please welcome Harry Claxton.
Hi. So thank you for the opportunity to showcase the recent successful completion of the first hexane diol project by Johnson Matthey. I'm a technology manager looking after a suite of related ester hydrogenation technologies, including the new hexane diol process. And this is also a finalist in the Innovative Product Award category, and I'll go into more detail into the chemistry and innovation process tomorrow. So Johnson Matthey are organised around shaping a new era of clean energy, achieving more from less, clean air for all, and helping people live longer and healthier lives. And it's a company I'm proud to work for. I work in process technology licensing, where the focus is now on improving the sustainability of producing the materials that we all consume. So hexane diol, it's used as a chemical intermediate monomer in polyurethanes, acrylates, and polyester resins. It can impart improved properties compared to other diols, such as greater flexibility and greater hydrolytic stability. The feedstock is adipic acid, which is readily available as it's used to make nylon 6,6. And this is the chemistry of the process. First, the adipic acid is esterified using an acidic acid resin. Esterifying the acid allows for cheaper carbon steel to be used in the hydrogenation section. The hydrogenation itself is performed over a fixed bed of catalyst in the vapor phase, which controls the temperature rise and residence times, leading to low byproduct make and maximizing the yield, as well as reducing the cost and energy consumption of the purification process. A less hazardous non-chrome catalyst is used for the reaction. And as you can see, that hydrogenation regenerates the methanol. So this just shows the overall process. The methanol can be used to dissolve the adipic acid, as well as performing the esterification reaction. The ester is then hydrogenated with hydrogen to hexane diol and methanol, which is separated by distillation, along with the other byproducts to achieve high purity product. The methanol is recycled back to the front end. A small methanol makeup is required to replace a small amount of methanol lost to byproducts. So within JM, we have all the skills and capabilities needed to develop a new chemical process, all the way through from concept through to successful operation. This includes all the steps shown in the blue boxes, from ensuring there's a market for the process, designing manufacturing catalysts, designing, building and operating process mini plants, engineering scale up and design, and licensing capability. Underpinning this are the internal procedures to ensure the work is focused and managed with appropriate checks and reviews. The hexane diol process development was a recent example where we were able to take a process from concept to successful license and start up in a very short time. JM had already licensed a dozen plants using our maleic acid to butane diol process, and we were able to adapt reactor technology that was used there, such as our proprietary esterification reactor concept. The esterification reaction is an equilibrium limited reaction, So for high conversions, it's necessary to carry out a series of reactions and separations over a dozen times to achieve the high conversions required. JM's reactive distillation column combines these via innovative catalyst separation and reactor technology, reducing footprint and enabling one column to replace multiple unit operations, a good example of process intensification. And the reactive distillation column was developed completely in-house. And this slide shows the development of the design from initial continuous tests and mini plant operation. And we also used hydraulic models to manage the scale-up risk, which meant we were able to go from a mini plant design to a full-scale commercial plant with a scale-up factor of 200,000. After initial benchtop test work, we were able to simulate the operation of the commercial process using mini plants. This slide shows some of the equipment for the esterification section mini plant. Commercial feedstocks are used and recycle streams closed to provide the data needed for the design. We need to develop a new hot solids handling system, drawing on expertise from our catalyst manufacturing specialists. Foremost, the design must be safe to operate, so the design is subject to increasingly detailed safety reviews as it becomes more defined. The left-hand picture shows the hydrogenation mini plant, again modelling the full loop and continuous operation on commercially representative feedstock to predict the catalyst life and byproduct mode. We also generated in-house vapor liquid equilibrium data and ran distillation columns to validate the distillation design and performed other test work such as corrosion testing. JM don't own or operate chemical plant, but have a licensing model instead. The technology transfer is performed via a basic engineering package that contains all the information for an EPC contractor to complete the design of the plant. Engineering services include reviewing detailed engineering documents, supporting HAZOPs and performing construction reviews. JM supply all the catalyst and some proprietary reactor internals. We then provide training and perform pre-commissioning checks and provide commissioning assistance to help successfully start up the plants. We've sold 2 licenses already for our hexane diol process. The first license was sold to Chongqing Yuan Li for a 30,000 tonne a year plant in China, which was successfully started up in April 2019. The second license was sold to Henan Shenma for the same capacity, also in China. We've just finished the basic engineering package for the second plant. Now, hexane diol is just one of a number of technologies which JM license, using a number of core technologies. Commercializing new process technology is hard, and there are many risks. Our extensive experience in developing and delivering licensed technologies was key to the successfully turning the concept of the hexane diol process into reality, using our highly skilled chemists and engineers. And I'm proud to represent them all at the IChemE Awards. So thanks for your attention.
Thank you, Harry. Thank you, Harry. Okay. Thank you very much. We'll once again pause for questions. You know the drill by now. Please get in touch via the questions box. And if you have been suitably inspired by today's presentations, it might be time to start thinking about your own awards entry for next year. Keep an eye on the IChemE Awards website for more details, but we plan to open for entries in early March 2022. We have still a few more finalists to hear from before we announce our award winner. So let me introduce our next speaker, representing the joint entry from National Institute for Innovation in Manufacturing, Biopharmaceuticals and Biopharm Operations Group. It's Kevin Gibson, accompanied by his colleagues, Paul Randolph, Don Chao, and Daniel Wiseman.
So I'll get started. I'm Paul Randolph from Janssen, and I've been involved in this collaboration between the National Institute for Manufacturing of Biologics and Bioforum for several years now. And this is really exciting, and I'm really pleased to be here to talk about it with Kevin and Doan. We've been working together on this for quite some time. And this is a bit unique because it's a collaboration in the industry where we've come together and recognized a problem that we all face, and no one has the ability to take it on their own. So by working together, we've been able to develop a solution that can solve this issue for the industry. So I'm not going to read through the whole abstract. I'll leave that for the future, but let's go to the next slide, and I'll get into the problem and how we solved it. So in therapeutic protein manufacturing, we use a lot of buffer, and a lot of our energy and time and effort goes into making buffer. So we're talking about producing proteins in biologic manufacturing made in cell culture. It's a very highly controlled process. It's all done in clean rooms. So to produce a ton of bulk drug substance in a year, it takes 83 bioreactor runs, and that requires 170,000 liters of media, and then about 10 times as much buffer to process that material and purify it. So the buffers are used on chromatography processes and other purification steps. Typically, a process would take about 17 unique buffers, and we'd need to make over 500 batches of buffer a year to support that. So it's a very intensive process. It takes a lot of footprint, in a lot of it's in clean room space, which is expensive to maintain. It results in high material consumption, a large impact on the environment, takes a lot of labor, and the logistics of managing that can be quite a challenge. Everything from raw materials, testing, preparation, and in the GMP world, these can add a lot of extra burden on the manufacturing, so that we have to prove everything and track it very closely. So ultimately, it ends up with bottlenecks in production and limits our capacity in the facility. You can go to the next slide. And oh yeah, so the point is, not much has changed in the industry in the last 20, 30 years. And that really gets back to the point of no one on their own had the ability to solve this issue. So in discussions in the bioforum, we've identified the issue and come up with some unique solutions. So looking at simplifying the design of the buffers and identifying the 4 components that are used to make the buffers, and then building sub-teams to address the gaps in the technology. And you know, the quote from Natalie here is pretty telling, that the facility of the future will not be possible if we don't find a solution to the buffer prep bottleneck. And that really highlights how important this was. So Bioforum had these ideas in the technology roadmap, and kind of laid out the blueprint for what to do. And then to take action on it, there was a partnership with in the US, the National Institute for Innovation in Manufacturing of Biologics, where we came up with a proposal to develop a project to fund and support actually building this equipment in the consortium, and involved members from both Bioforum and Nimble from a number of different companies. And through that project, we designed and built and tested this equipment. And so we'll go into some of the details about that, and I'll pass it off to Don Chao here, and he can talk more about how that came about.
Yeah, thanks, Paul. So as Paul mentioned, there was an industry challenge, and we were trying to tackle that, right? So why were we trying to do this? We were trying to increase the adoption of this technology within the industry. So the democratization of the technology is a big driver for us, right? Additionally, we wanted to make sure that we try to reduce cost for the industry. Again, as Paul mentioned, the making of buffers was very labor intensive and very costly in terms of labor and material, and really the footprint required in a biopharmaceutical plant. Because no one could do this alone, the team came together, and we wanted to demonstrate that proof of concept by really actually building this kit and making it available for everyone to take on and adopt it within their plan. move on to the next slide. So this is a picture of the skid that was fully built and developed. It was built with a full GMP design in mind, from a hygienic clean room design made to be fit in a clean room environment, as well as a fully kind of commercial automation platform made to be fit in a GMP environment to meet FDA Part 11 compliance and other good automation manufacturing practices. It was based on mass flow recipe-based control, and that's in comparison to pH feedback control. It was made to be flexible, so you can connect it to bags, to tanks, or directly to a chromatography or downstream chromatography skid. And it's made with modern automation controls, and the design and the documentation open source for development of future skids. When it is adopted by other customers, it can be easily adapted and configured to meet the specific customer and user requirements and needs. It was modeled off of a monoclonal antibody process. So size for a 2,000 liter single-use bioreactor with 16 stock solution inlets. Next slide. Summary of our achievements: the collaboration across Nimble Bioform and across the multiple companies involved was absolutely amazing. It's something that I'm very proud of. This collaboration over 2 to 3 years across 4 different time zones, many meetings in between. So it was a huge effort across all individuals and organizations. Over that time, there have been several white papers published, and one more white paper addendum to be published in the future with a full data set available. As said, the skid's been fully built. It's also been fully tested with a factory acceptance test at the factory site, with some more testing done at the University of Delaware, the Nimble building. Some of that testing was realization testing and demonstration testing, all just to provide documentation, a data set available, so that way adoption of this could be easier. People understand that this is something that's true. It meets what we designed it to do, right? And it's made to make buffers quickly and more agile than in the past. It's currently right now at the University of Delaware in at the Nimble headquarters, where it continues to be tested and continues to be shown by member companies within Nimble and Bioforum. Next slide. When we first tested this, our initial impressions were that the speed was an absolute game changer. The time it took to make buffers was significantly less than what it used to take in a traditional setting. In a traditional setting, it used to take 1 shift to make 1 buffer per tank. And if you saw the amount of tanks available in a factory, in a plant, it's massive, right? It's several tanks, much larger than the skid, right? And it takes a lot of manpower, a lot of effort to create 1 buffer. What we found was the speed was significantly less. We made buffers in minutes compared to hours over a shift. Right? And we saw that this was very efficient. It was pretty much about 95% efficient, even more efficient for larger scale batches. So at this point, I'll hand it over to Kevin to talk more about the impact on the industry.
Thanks very much. I suppose the use of the buffer stock blending system will have a significant impact on facility design and operation. So as Dylan mentioned, one of the key advantages is you reduce the number of preparations required significantly. So rather than producing, say, 20 buffers a batch, you're going down to a much smaller number of common single component stock solutions. So you reduce the amount of preparations you need in half, or even more so. That in itself has a massive impact on the labour for buffer manufacture. So buffer is one of the most labour intensive areas of biopharmaceutical manufacture, and this addresses one of the key areas. In addition, because of the single component nature, you can reduce the volume of liquid to be stored and handled significantly. And in the case of, so in a traditional buffer prep, you're prepared in a tank or a bag, you're transferred into a whole bag or tank, and then you transfer it to, say, your chromatography process. In this case, you have the option of going direct to your chromatography system and eliminating the need for buffer hold completely. Given the amount by which you reduce the volume of buffer to be handled, it allows much greater single-use utilization at a large scale, which in itself increases flexibility and reduces capital costs. I mean, overall, for every scale of manufacture we've looked at, whether it's a 2,000 litre single-use scale or a large stainless steel facility, the overall total cost of buffer is reduced considerably using buffer stock blending. And that's primarily down to the operational savings. Although once you get into a large stainless steel facility, there is capital cost savings also. I think it's fair to say if it's every single scenario we've looked at, it has a benefit. It's just the relative benefit can vary by scale. As we're going through in conclusion, so traditional buffer prep occupies a significant amount of labour, capital, footprint and time. As Paul mentioned at the start, so Bioforum identified the potential for addressing this as part of the technology roadmap and identified as a key industry challenge. As a group, we come together and we came up with some ideas of how to resolve the issue. And then Nimble funded the design, build and testing of the BSP skid. And the outcome of that really shows is that the skid works extremely well. We're able to produce a very wide range of buffers in real time. And one of the key features of this project, which makes it unique, is the design and the data set from the testing is going to be released open source. So it's really a case of the industry coming together to solve a common problem. And we're putting that design out and making it publicly available so this can be implemented and have accelerate the impact on the industry. I suppose we mentioned the collaboration across the industry, and there's too many companies and names to go through, but on the screen now gives you an idea of the number of companies and individuals who've been involved in the project. So it really is a case of a way as to the whole industry coming together to solve this problem. And obviously open to any questions if there is any.
Thank you very much for the presentation. We'll now move to question and answer. So if you have a question, please type it into the question box as usual. I will give you a moment for that. We don't appear to have any questions. So thank you again, everyone, for the presentation. And we have reached now our last presentation of the day. From Saudi Aramco, please welcome Hessam Zer.
Hello, can you hear me?
Yes, we can.
Yes, good day, ladies and gentlemen. Please allow me to start by introducing myself. My name is Hisham Zahir, working with Saudi Aramco as an operations advisor. Today, it is my great pleasure to share with you one of Saudi Aramco initiatives toward achieving zero flaring at our facilities. Here is the outline of my presentation. I will start by shedding some light on gas flaring. Then I will move to the current conventional technique for oil well reviving and boosting, followed by the invented approach which I'm presenting today. After that, I will conclude my presentation by the benefits we are gaining from this invented approach and its advantages. Before we go any further, I would like to introduce the inputs and outputs of our gas oil separation plants, GOSP. The GOSP receive crude oil from multiple oil wells scattered in the field. Inside the GOSP, the crude oil is processed and separated into three main outputs: processed oil, compressed gas, and produced water. To maintain the safety of our personnel and equipment, we have gas flares to safely burn any excessive gases. So, flaring is the controlled burning of unwanted exhaust gases to enhance safety. Although gas flaring is important for safety reasons, it has many drawbacks, including negative impact on the environment, primarily due to incomplete combustion of the gas and the waste of potentially useful resources. The crude oil that gas oil separation plants receive come from several wells, different characteristics. Over the years, some of these wells may deplete and require boosting and reviving. This exercise, reviving and boosting wells, is common in the oil and gas industry, and it results in unavoidable flaring. So we have a conventional practice that we commonly use for this vital activity of reviving and boosting wells. We also use this conventional practice for well testing and flow line depressurizing. Ladies and gentlemen, as you can see in this figure, in the conventional practice, we utilize high pressure test trap, HPTT, which is a pressure vessel inside the GOSP. So, to boost and revive dead wells, the pressure in the HPTT is reduced until a sufficient differential pressure between the reservoir and the vessel is achieved. This allows natural flow of crude oil to the GOSP. However, in some cases, the HPTT low pressure will not allow processing the gas, which leads to flaring. Therefore, we realized that an innovative approach that would eliminate gas flaring in all cases would be very valuable to protect the environment and increase the revenue. So, ladies and gentlemen, we reached to my favorite part of this presentation, which is the invented technique. Basically, the idea is to install a multi-phase ejector that capitalizes on the existing infrastructure and available resources at the GOSP by utilizing the high pressure of the shipped crude as a motive source. This motive source is used to stimulate dead and weak wells to flow. As the low pressure source from dead and weak wells meet the high pressure source from the shipped crude, they mix inside the ejector. The mixture, which has an intermediate pressure, will be diverted for further processing without any flaring. So, the working principle of ejectors is very simple. First, a high pressure source is needed. Once the high pressure source passes through the ejector, its pressure will significantly drop, resulting in a sonic velocity at the neck and supersonic velocity at the exit. This will create a low pressure area that can stimulate the flow from low pressure wells. After that, this high velocity flow, along with the oil from the low pressure well, will pass through the other part of the ejector, which is another converging diverging nozzles. And the other part the velocity will drop and the pressure increase to an intermediate pressure sufficient to divert the mixture for further processing. Moving forward, the invented technique has the following benefits and advantages over the conventional practice. First and foremost, it eliminates the reviving associated flaring. Furthermore, it increases the production by boosting low pressure wells. In addition, as opposed to the conventional technique which require pumping, the invented approach is more energy efficient because it only uses an ejector, and ejectors are static equipment that utilize no energy. Last but not least, it is maintenance free, as ejectors have no instrumentation or rotating parts. By this, we are able to participate in embracing a circular carbon economy by reducing carbon footprint while increasing energy supply to the world in safe and environmentally friendly manner. This brings me to the end of my presentation, and I will be glad to answer any question you may have. Thank you for listening.
Thank you, Hessam. So for the final time today, we'll pause for questions. If you would like to get in touch, please do so via the questions box. We don't appear to have any questions, so thank you again very much, Hessam. It's time to move on, and we have reached the moment that we've all been waiting for. It's time to find out the winner of the IChemE Industry Project Award, sponsored by Silverfield Limited. Before we do that, I'd like to thank all our finalists for joining us today and for taking the time to share more details about the fine work. I'm sure you'll all agree, a fine, diverse range of work on show. Let's start by announcing our highly commended entries, and they are the joint entry from Dow Polyurethanes and Cell Foam Solutions and Johnson Matthey. Well done to everyone associated with those projects, but now it's time to announce the award winner, and for that, I'd like to hand back to Silverfield Limited's Elizabeth Cook.
Ladies and gentlemen, the winner of the IChemE Industry Project Award, sponsored by Silverfield Limited, is Corteva Agriscience.
Congratulations to everyone who worked on the winning entry. Greg, I hope you can tell us how does it feel to be an IChemE Award winner?
Thank you very much. I'm honestly shocked given the quality of the other finalists and their presentations today. So I'm very very thankful for the recognition for Corteva Agriscience and what we're doing to try to improve the sustainability of agriculture. So thank you very much.
Well, congratulations once again. And thank you everyone for joining us today, especially all our finalists and of course our sponsor, Silverfield Limited. We have still plenty more IChemE Award webinars to come over the next few weeks. We will be back tomorrow to announce the winners of 2 more awards, but that's all for now. Thank you very much for joining us. Goodbye.